fairly simple kind of form of problem, but yet it's capable of capturing a lot of rich and complicated physical behaviors, and it brings in a wide variety of mathematical techniques that you need to kind of describe all of that. So it's a kind of encyclopedic story. So this is going to be about fluid dynamics at its core, but basically everything is going to be in terms of different approaches for studying a PDE problem, describing, so here are numerical simulations. So they start off with a fluid layer coating a solid surface, and then the fluid layer breaks up into some patterns that eventually become droplets. And I'm going to talk about the whole history of what happens from beginning to middle to the end. And that's going to involve different mathematical techniques on the different behaviors and different length and time scales. So, the talk will be structured in those three portions, and just because we're constrained for time, the amount of time I'll spend on them will also kind of directly correspond in some way. So, no pun intended, but okay, so let me launch into the physical background and description. So these are experimental pictures done by other groups of what's called dewetting behavior. So if you have a hydrophobic or water-repellent surface, then, so it's, imagine a Teflon-coated frying pan or Gore-Tex fabric. If you spill water or oil on it, then it doesn't want to keep spread out. It wants to bead up. For example, rain on the hood of a waxed car, or just wine on the hood of a waxed car, or just water on wax paper from a deli. So fluid, a uniform layer tends to break up into. First, it forms holes, and it forms point rupture, and then they grow into holes. The holes broaden and form more complicated patterns, and then the fluid kind of spreads out, and then you have these polygonal ridges, and then those ridges themselves become unstable into arrays of droplets. And then, so I'll talk about this whole scale. So the time scales involved here. Experimentally, they vary depending on what kind of materials and what kind. But the size here may be impossible to read, but it's like 5 microns. So these are small-scale experiments where surface tension can become important. Material science is definitely important because the material properties of the fluids and the solid surface they're spreading on can become very important. Okay. So first, the classical fluids background. So this is going to be a thin fluid layer spreading on a flat solid surface. We start with the Navier-Stokes equations, and we're going to consider slow viscous flows. So I'm going to drop the inertial term, reduce the Stokes equations immediately, and then I'm going to also consider that this is a long layer of a very shallow film. So there's going to be an aspect ratio parameter, which I'm also going to use as an asymptotic parameter to further reduce Stokes equations down to what's called the Reynolds lubrication equation, which is just a single evolution equation for the height of the fluid layer, every place in terms of a divergence of a material flux, which is given in terms of some kind of pressure times the mobility coefficient. So this is a very kind of generic form of transport PDE. And let me just kind of briefly kind of relate the problem I'm going to be talking about to just like other related PDEs that you may be more familiar with or have studied. So the mobility coefficient comes up in different problems in fluid dynamics and material science, but the classical one in fluid mechanics involves like no slip boundary conditions on the solid surface, and at the free surface there's no shear condition, which gives you an h cubed for this coefficient here. There are other forms of problems which give you different power laws for like polymer materials spreading on the surfaces. But most of the attention has to be on what physics you capture in the model by describing the dynamic pressure as a functional of the height. So the simplest model is if you just have hydrostatic pressure. So the pressure is based on the height of the fluid column that you're looking at. So then what this equation reduces down to is called the porous media equation, which is a classic nonlinear degenerate parabolic equation for like honey spreading on a solid surface, or lava flows are also sometimes described like this. And there are many interesting properties, including the famous Baron-Blatt similarity solution, which is a nice textbook example. It's also an example of a weak solution with finite speed of propagation. That's a second-order degenerate
Tom,
diffusion.
can I ask you a question?
Sure. Yeah.
So I think is honey and lava, are those Newtonian fluids?
Good question. So honey might be, lava definitely not, but there are non-Newtonian versions of this too, of this kind of equation, but they're messier. They would generalize the mobility coefficient to possibly depend on not just the height, but also gradients of the height, and also the pressure might also depend on nonlinear combinations of the gradient. And then if you have viscoelastic effects, then you'd have this equation coupled to another evolution equation for a stress.
Okay, thank you.
Yeah. So if I neglect the influence of gravitationally driven spreading and focus on another influence of what present where we have a free surface, which is the curvature, or surface tension, then the pressure becomes, pressure has a contribution from the curvature of the free surface with some surface tension coefficient times it linearizes to just the Laplacian of the height. So that gives us this fourth order equation, which is called the thin film equation. And so this is a big brother to the porous media equation. It's more complicated because some of the nice things in terms of like a maximum principle and other things about existence and uniqueness of solutions that you can prove for this become non-trivial questions for this. But this is the kind of fundamental model that's used a lot in fluid dynamics and engineering and chemical engineering, and so this is the basis of like these thin film models I'm going to talk about. So one of the other contributions that's important to add into the physics of this for the pressure is the influence of what the fluid understands about what the solid surface is. So if I give you just a generic fluid on a generic solid, it doesn't know, there's no description about whether the surface is water repellent or attractive to water. That's attractive is hydrophilic, repellent is hydrophobic. So hydrophobic wants to have the water beat up and stay like this. So this minimizes the energy, whereas a hydrophilic surface wants the water to spread out and coat the whole surface. And so the way to capture this difference between material properties most simply is through what's called adding a disjoining pressure, or an intermolecular potential between do molecules of the fluid want to attract each other preferentially or attract to the surface preferentially. So this is given in terms of a disjoining, a potential energy function U of H, and the gradient of that with respect to height gives us what's called a disjoining pressure term. And depending on the sign of that, we can describe either hydrophilic or hydrophobic materials. So just keep in mind, it will always be basically of this form. And this is the leading order approximation to what this is. You can derive this in a kind of straightforward way from looking at particle interactions. So now I'm ready to assemble the pieces to give you the PDE that I'm going to talk about for the rest of this. So I'm going to consider the standard mobility coefficient, the h cubed, which goes over here, and then the gradient of the pressure is going to have these two parts: surface tension contribution and this intermolecular contribution for me describing hydrophobic materials, because ultimately I want to talk about what happens and why it's interesting when the fluid is going to break up and beat up into droplets. So this is the model overall, and it has your basic kind of properties that you'd expect from an equation written in divergence form. So this is divergence of stuff inside. So it's assuming I have no flux boundary conditions, I'm going to have conservation of mass. This equation also has an energy that I can write down basically in terms of potential and kind of like kinetic or surface or interfacial energy. So this energy is monotone decreasing, and it's written in terms of the mobility coefficient and the gradient of the pressure squared. So these are nice properties, and they will come back for some of the theory I'll talk about later on. These two things are an important ingredient. And also, this equation has an important feature it shares with many other types of PDEs that have been studied in other contexts in material science and other things, in that the fourth order surface tension tends to be a regularizing effect. It tends to smooth things out and reduce energy by having solutions that have small gradients, while the second order term tends to destabilize things and create interesting patterns and other behaviors. So this, and we'll see that this can create finite time singularities, or there can be global existence depending on what function you have here and what function you have here. And we'll see some of these interesting effects between the competition of these terms in this equation, but similar things come up when you study the Kahn-Hilliard equation in material science, or Koremoto-Shibashinsky, Swift-Hohenberg, or other PDE models that are used in pattern formation. Okay. So part one, the early time behavior. So what happens if you start with a thin film that's flat, and I look at small perturbations of that. So I'll try to linearize around the flat state, add the usual kind of separation of variables or stability analysis to infinitesimal perturbations, spatial oscillations in space times exponential growth rate. Plug that into here, we get a dispersion relation that that has growing modes for small wavelength, but for large enough wave number, eventually the surface tension term stabilizes everything. So there's going to be a finite band of instabilities, and we find out there's a critical thickness also. At that critical thickness, there's a byte that this value, depending on the square root of the length of the domain divided by pi, this is a bifurcation. Films that are thinner than this are going to be unstable. Thicker films are going to be stable to infinitesimal perturbations. But films that are thicker than this will also have another set of unstable equilibrium solutions. So here is this solid curve, this darker curve that I marked here. Is an unstable equilibrium. It's spatially periodic, and if I perturb it slightly, if I add plus epsilon to that and use that as an initial condition in a PDE simulation, I'll see that that unstable initial condition will relax towards a stable flat film. But if I take that same initial condition and perturb it in the opposite way, subtract epsilon everywhere from that, then instead of relaxing to the stable flat film, it will actually rupture in finite time. So that's clearly an instability that's different than the perturbing in the neighborhood of the flat state. But this family of periodic solutions bifurcates off the flat states if you're at this point, if you're at this critical thickness.
Question, quick, on these perturbations, these deformed states. Are they linear, or is this a finite amplitude instability that you're investigating there? Is that?
So this result I've written here was just infinitesimal perturbations to the flat state, but I'll talk about the perturbations to these finite amplitude unstable states.
Okay. Okay. Thanks.
So the dynamics leading to this rupture, this finite time singularity. I can actually do the similar kind of stability analysis of these unstable finite amplitude states. Then I'd have to do the analysis kind of numerically or with some variational approach. I can't quite do it analytically as simple as the flat state, but I can show that these are unstable. And in a small neighborhood, you'd see some unstable modes, but I'm going to consider the nonlinear behavior following the instability, and that can be shown to be given by self-similar solutions. So these are going to be first-kind self-similar solutions where just by kind of scaling analysis in terms of the height scale versus the length scale and setting a time scale in terms of the time until rupture, you can find that there's a scaling relation where the height scales like square root of the width of this rupture point. So this will like a square root kind of cusp as it comes close to touching down. And by plugging in this ansatz into the PDE, you can find that it reduces to a self-similar ODE. So you can effectively, this gives you a nonlinear separation of variables between this time scale and a spatial profile given by this fourth order PDE. And the boundary conditions effectively say that while dynamics are approaching a singularity in this neighborhood of this point, in the far field, everything is kind of slowing down relative to this time scale. So far away, it looks quasi-steady. So say a little bit more about this, but this is the short time early regime. So that you can study the stability of these self-similar solutions too, following some classic work by Giga and Cohn from the 1980s. So if you consider this the problem as some general nonlinear PDE, the similarity solution is actually going to be a steady state. If you change to similarity variables like the eta that I introduced before, and also a new time scale given by the log of the usual time, then you can rewrite the original PDE in terms of a new PDE in terms of these similarity variables. The self-similar solution is actually a steady state of this equation. And as a steady state, you can do linear stability analysis to infinitesimal perturbations of the similarity solution. So in these variables, these perturbations, they look like exponential growth or decay, but in terms of normal variables, they're actually going to be kind of algebraic growth or decay as you approach the critical time. But once you've written this, you can write down the usual kind of separation of variables and calculate the spectrum in terms of eigenvalues and eigenfunctions, and that will show that there is a stable self-similar solution in 1D. There's actually a family of different similarity solutions, but the first one in that discrete series is the stable, and that's what's going to be observed in numerical simulations. In 2D, those 1D similarity solutions, which look like rupture along a line, are actually going to be unstable, and the solutions will actually be unstable to perturbations that lead to rupture at points. Okay, so this is what happens on short times. The downside of this model is that after rupture happens, you can show that you can't continue the PDE. But so that's unphysical, but there's a way to change the disjoining pressure to add another term that kind of more accurately represents the physical behavior, and then lets you continue the solutions for all times, which we're going to be interested in. So I'm going to add one other term to the disjoining pressure that balances out the term that tends to lead to rupture. When we reach a finite scale epsilon, so a thin film layer will remain, and that will be a lower bound on the solution, but it will mean that solutions will exist for all times. That they will basically behave the same way until they reach this minimum thickness epsilon, and then after that they'll do something interesting. Okay, so the part two, the intermediate stage. So after thin film has kind of gone unstable and approached rupture, what's going to happen is instead of really reaching rupture, it will stop. It will be bounded from below by epsilon, and instead of kind of like the PDE simulation stopping, what happens is that that point rupture opens up and forms a hole that widens. And so you'll get effectively like a parting of the Red Sea. There'll be a empty, almost dry layer while the fluid gets pushed to the left and right of the hole. And so hence you'll find a lot of papers studying these growing dewetting rims that counterpropagate to open up a hole, a dry spot in the middle. And there are many studies that have gone into doing asymptotics and numerical simulations of these moving contact lines. And if you have more than one rupture happening in a domain, so here you'll have a hole opening up, and here you'll have another hole opening up, and the counterpropagating rims will eventually collide and form droplets where all the fluid is collecting while the surrounding areas are all effectively dry except for effectively a nano-layer thin fluid layer. It's still going to be connecting one droplet where all the mass is to droplets that are kind of isolated from each other to a degree. And so this is kind of how things transition from the original state.
I have a question about that. Does does the previous slide then seem to indicate that the droplets that form should have a wavy profile, or?
So I'll talk about the droplets that will. So here you can see that there are these two kind of this peak propagating to the right and this peak propagating to the left come together, and eventually they will kind of convexify to form this droplet.
I see.
So I'll talk about the exact shape of the droplets, or the asymptotics lead to a very nice simple description of this droplet shape.
Thank you.
But the intermediate dynamics can be quite complicated of the PDEs. So we started from these thin films, then they've gone through this rearrangement of the fluid mass into these kind of what they look like castle walls, and then these things break up into these individual droplets. And there are many different ways this can happen, and the instability, this intermediate range is studied by a large number of people too. But I'm going to focus most of my time today in the talking about the long time behaviors. So after this, so this breakup of the fluid layer into these many droplets is now going to set the initial conditions for the final stage, the long time dynamics. So we're just left with several droplets kind of separated by these thin layers. And the droplets are going to be now kind of fairly stable and close to equilibrium locally. So we're going to see how they interact with each other. But each droplet is going to be close to equilibrium. And so I can first look at, okay, what are the equilibrium solutions of the original problem? And actually, so that's given by setting the pressure equal to a constant. That reduces the fourth order PDE down to just a second order phase plane. And a droplet profile is actually going to be given by a homoclinic solution of this second order phase plane equation. So starting from that thin layer, epsilon, an excursion, and then back to that. And I can do asymptotics of this equation for epsilon goes to 0, and then I can actually very nicely describe the core of the droplet as being parabolic in profile. And there's a boundary layer that matches from the flat layer to this core, and that picks out this angle here, which is called the contact angle, in terms of the specific form of this disjoining pressure function. So this contact angle property, which is a very important thing about like fluids and characterizing fluid interactions with solids, is kind of directly connected to what form of this joining pressure that you use. So having this parabolic form is a nice simple description, and it lets me relate the height of the droplet to the width of it, and also get a simple form for the mass contained in the droplet in terms of the pressure. So I have a simple relation between physical property I'd like to describe of the individual droplet, its mass, relating to the pressure, which is a field that we had that we formulated the original PDE in terms of. And the pressure is something that exists everywhere in the domain. And that's going to be a useful connection between something spatially localized and something that's defined everywhere in the domain. So let me go back to the PDE and think about starting with a single droplet and putting it on a finite domain. And imagine, so it's already going to be perturbed because homoclinic solution wants to live on an infinite domain. I also want to perturb it by having the influences of some boundary conditions at the finite domain, like what happens to the left and to the right if there's some mass flux pushing on the droplet, pulling away fluid. So I'm going to have a couple of sources of perturbation on the drop, and I want to see what are the dynamics like. And I'm going to put a small parameter, sigma, that's going to set a slow time scale for the evolution of the drop. I expect if I start from a parabolic drop that I will continue to evolve as a parabolic drop, except I may grow or shrink, which means my pressure may change because corresponding to my mass, and depending on what forcing I have from the left or right boundaries, the droplet position may change. So I imagine I can have these two parameters, x and p, that will give me this two-parameter family of quasi-steady solutions. And those will be functions of a slow time variable. And then I can plug this in along with higher order perturbations in terms of this parameter sigma plug that into the PDE and do an expansion to find out amplitude equations that will determine these. Questions? Or did grad students know this back and forth already, I hope, from their courses there, right?
Right.
Okay. Okay, I'm going to go with that. So at leading order, plugging this in, I find out, okay, I need the leading order to be a solution of the steady state. I already picked that, so yes. Moving on to next order. At order sigma, I'm going to have, taking the derivative of my assumed leading order form, I'm going to get derivatives of these slow time variables and the linearized operator for the spatial stuff on the right-hand side. So my spatial operator is the Frechet derivative of the nonlinear operator. And I need to think about what the properties of this linearized operator are, linearized around the droplet state. I know that the translations of the droplet are all solutions for any position. So this thing has one null mode based on me translating the solution. So that's going to be a derivative of the droplet profile. And it's going to be another null mode based on me having a continuous family of drops of every possible mass or pressure. So I have these two functions in terms of the droplet profile that are going to be null modes of this operator that appears on the right-hand side here. So I have linear operator equals some inhomogeneous term. This is a good place for the Fredholm alternative. So in order to get existence of a solution, I need a solvability condition, meaning that the inner product of this side against these null modes has to be 0, or at least bounced by the boundary conditions. The boundary conditions are given by in terms of those fluxes I'm applying. And this is actually going to determine these two projection onto these two null modes gives me two equations. One evolution equation for how the droplets move to the left and right, another one for how the pressure changes, or equivalently how the droplets gain or lose mass with time. And these were evolution equations on the slow time scale, but I'm able to kind of rescale everything to be in the original time scale of the problem. So now I've reduced the PDE for droplet evolution just down to 2 ODEs. And these 2 ODEs have simple modes that I can interpret in terms of like translating as like a traveling wave if I have the appropriate fluxes pushing and pulling, or if I have pumping mass in or out, I have a changing position. Now that I'm in changing position. And now the important thing is I don't want to study just one drop. This is a building block. I really want to study interactions of droplets due to interacting with their neighbors. So instead of having imposed fluxes as artificial boundary conditions, I want to study the influence of one drop on the fact that it will have neighbors at some finite distance away, imposing some mass flux into or out of a drop. So I imagine I have a set of droplets on a domain. If each drop is close to equilibrium, then each drop will have approximately a constant pressure under its core footprint. Between those constant pressures, there'll be approximately a linear connector between them, but those connectors for the pressure will correspond to very thin films that will be quasi-steady. And those will kind of limit how fast the fluxes can be. So I can guarantee that I'm always close to equilibrium. So this builds up to the bigger picture of the dynamics for long times. And a quote I like, I don't remember where it came from anymore, but complex systems can be locally close to equilibrium, meaning each of these drops by itself is almost in equilibrium, but globally the system is complicated and has interesting dynamics because globally it's far from equilibrium. The equilibrium solution has constant pressure. Here I have droplets that have larger pressure, smaller pressure, so I can have bigger or smaller droplets all connected to each other, and how they evolve is actually not trivial or not obvious to see just by looking at this. Eventually it's going to go to a constant pressure equilibrium. We know that from the energetics of the problem, but in order to see how this plays out, we're going to have to follow the evolution of this. So the fluxes are going to be limited through these thin films between the droplets, and we can define basically a chemical potential. The fluxes are going to be given by minus the spatial gradient of a chemical potential. So I'm going to assume that happens in a quasi-steady way. And this potential V, that is actually going to be that actually is going to be the thing that's linearly defined between them, because this satisfies effectively Laplace's equation between them. So this function gives me a convenient way to define the fluxes in terms of the chemical potential at the edge of one drop to the chemical potential at the edge of the other drop, separated by the distance between this contact line position and that contact line position. So this is a very simple kind of approximation. It's messy looking, but it's basically delta V over delta X. And this gives me the definition for the fluxes between each pair of drops. So I can now write a system of coupled ODEs for the evolution of each drop due to its nearest neighbors. So this gives me a set of 2 ODEs for each drop, and this gives me describes the drops as effectively an interacting particle system for these localized structures. So in other problems, the localized structures may be moving interfaces or other things, but here my droplets have good properties for these droplets that have 2 properties, position and size. So these ODEs, you can imagine evolving them as far forward in time as they go, but this particular form for the flux has a dramatic behavior in that the equations can go singular with the flux diverging at finite times if one of 2 things happen. So if the one drop can either collapse or melt as its mass kind of leaks out into the surrounding area, that will cause the flux to diverge to infinity as the pressure goes to infinity. So that droplet will effectively disappear in finite time. Or another dramatic thing that can happen is 2 drops can actually collide and merge into each other. That will also cause the flux to diverge in finite time. And both of those things dramatically change the system in terms of having nice, smooth, slow, near equilibrium behavior to having a sudden and dramatic event where I need to change the system by removing the drop that died or taking these 2 drops that merged together and replace them by the new drop. So this is actually an example of what's called a hybrid dynamical system, where for long stretches of time you have dynamics given by slowly evolving amplitude equations, and then punctuated at sometimes by dramatic events where you need to stop the system, figure out the final state, look at the final state, and then map that onto a new initial condition that, let's say, conserves the mass and puts a new drop to replace the 2 previous drops that were there at an appropriate position, and then you restart the ODEs again, and this system of reduced number of drops evolves slowly until the next kind of collapse or collision event. So this is a system where you have, like, you start with a large number of drops, and then you reduce by 1, and you reduce by 1, and so on. So this kind of behavior happens in many kinds of systems, including image processing, where if you keep smoothing an image, you reduce edges, or you reduce the level of detail and resolution. It also happens in material science, or hyperbolic PDEs, maybe where you may have a large number of shocks in an initial condition, but the shocks may kind of run into each other and merge to form fewer but larger shocks. So this is called coarsening behavior, and it's the kind of the main dynamics that happens in the long time dynamics of this. So let me just describe a little bit more about how this collapse event happens for a single drop, and why it's going to be clear that happens in finite time. So as this collapses, it's losing mass to its surroundings, to the thin film, and to its neighbors. But the neighbors aren't really changing dramatically while that's happening. So I can effectively assume everything else is quasi-static and just look at the pressure evolving for that one drop. And I can by making some approximations, I can reduce that ODE to this based on the length scale to its neighbors and the droplet's pressure. And that does indeed give me a pressure that blows up in finite time, and it's actually cut off at some maximum value which corresponds to the minimum size quasi-steady drop. So this does correspond to a pressure, I mean, a droplet that vanishes in finite time. And I'm running shorter on time than I imagined, but there is a very simple heuristic scaling argument in terms of the mass scales and masses and the time scale set by this in terms of relating the pressure to a mass of the drop. Assuming all of the drops started off about equally, you can figure out that if there's only collapsing droplets, no radical movement of them spatially, then assuming independent and uncorrelated collapses, the number of drops is going to be given by a statistical scaling law, a power law that looks like t to the minus 2/5. So you can predict the number of drops based on how far forward in time. So this is like a numerical simulation of the ODEs that started with like 10,000 droplets and letting coarsening events happen, and eventually you see that after some startup period, eventually the number of drops decays steadily according to this power law. So there's been based on the kind of conservation of mass and the dissipation of energy, Cohn and Otto have shown rigorously with a PDE approach that there can be bounds on this kind of coarsening rate, or average coarsening rate. They studied that for the Cahn-Hilliard equation, but their results can also be applied to this problem and give this prediction, which kind of matches very nicely with the numerics I had done with Karl Glasner.
Can I ask a question about that?
Yep.
So initially the problem was you have a wet surface and that starts beating up into first castle walls and then individual droplets. I would assume that there's a limit to the amount of merging of droplets you can get, because if everything merges, then you're kind of back where you were, and you would expect that the dewetting would start again.
So I will. That's a very good question, and I'll talk about that at the very, very end. But in this model, there actually is no gravity. So what will happen is you start off with a layer. You start off with a layer on a large domain, and it will break up into droplets. Each one looks like a small parabola, and then the parabolas will merge with each other successively to form larger and larger parabolas. At the end of the day, you will get all of the mass that was originally in the film in one big parabola, someplace in your domain. So the final stable equilibrium will be a single parabolic droplet someplace in your domain.
And so that's not physical because you did ignore gravity to get there.
Right. So if you include gravity, what will happen is you will end up with these parabolas being flattened to form. Flattened at some maximum height, they will form, instead of large parabolas, they will be pancakes or puddles. And then those puddles will be stable. They won't try to remerge again.
Right.
And they won't try to remerge further, and they won't be unstable to perturbations. So they won't try to coarsen up or break up either. But that's a very good point.
Thank you.
Okay, so the equations I showed earlier, or these forms here, are a bit messy, and in order to get some more analysis or understanding of what's happening in this long time behavior, I want to simplify things and also try to think about the system more discretely instead of using the PDE theory at a continuous level. So can I use the fact that I've derived these ODEs for the individual droplets to kind of get an understanding of this dynamics and this scaling law? And also, what can I tell you about the distribution of droplet sizes as this process is continuing? So I'm going to simplify things out a lot. I'm going to assume that the droplets don't move left or right; they just grow or shrink in place, and so the positions of them won't change unless one of the droplets disappears. Then I'll update the length scales between nearest neighbors. But otherwise, I'm going to assume the length scales are fixed between just based on nearest neighbor positions that they started with. And I'll assume that the droplets are narrow compared to the wide separations between neighbors. So this allows me to simplify the fluxes down to this, and then I'll further simplify this by saying I'll take this chemical potential to just be linear in the pressure, and I'll relate the pressure back to the mass. So I'll rewrite the ODE for the pressures to be just a simple thing in terms of the masses of the droplets. So the mass of a drop evolves according to 1 over square root of its own mass and the square root, 1 over square root of the masses of its nearest neighbors. And this is still messy because I have lots of coupled nonlinear ODEs now. I can further reduce this by trying to write a mean field model where I'm going to replace all of the neighbors of all of the drops by an average sense of what's this property, what's this pressure that the nearest neighbors give effectively to it. So I'll replace the lengths by an effective average length scale between droplets, and I'll replace the masses or pressures due to the nearest neighbors by a weighted average mass based on what. Let me take the average of all of the 1 over square root of m's of all of the droplets, and that's going to be how I treat the neighbors' influence on the evolution of each drop. So this is now something that's decoupled from the neighbors, but effectively is non-local because I need to take stock of everyone's average, but this will tell me how each droplet will evolve by itself. So this is called the discrete mean field model because I'm still going to calculate the evolution of each droplet separately, but they're now globally coupled instead of coupled by nearest neighbors. And the collapses will happen at discrete times. And let's see, I'm going to show a plot of that happening. Yes, but first, I want to kind of transition away from kind of keeping track of all of these details to, I don't want to keep track of all of that microscopic information drop by drop. What can I understand if I have a macroscopic domain and I have a lot of droplets? Then I can think about considering the distribution of droplet sizes. So like, let me say I have a distribution function at a given time. So how many drops do I have of a given mass? So this would be like a PDF of different droplet sizes. But in this case, if I integrate over all of the masses, this is going to give me the number of drops. And if I integrate the this distribution function times the mass, and I'll get the total mass of drops in the system. So this is kind of using a classical framework in material science by Lifshitz, Liaushoff, and Wagner, dating back from the 1960s, used for Oswald ripening and other things in solids. But this distribution function satisfies a conservation law for conserving the mass. So I will get an evolution of this distribution based on the flux, or the rate, basically the rate of change of mass of an individual droplet. So that goes into this flux term describing, do droplets grow or decrease in mass? So this fits into here, and I've kind of, where did I get this from? This is just exactly the same equation that I derived on the previous slide for the interaction between individual drops. So this is like just a first order hyperbolic conservation law, except that this velocity is very non-local in that it depends on this integral over the whole distribution on the whole domain, over the whole domain. So this is evolution over the range of masses of drops. And so I have to have, so the average of this 1 over square root of m is given by the weighted average of that with respect to this distribution function divided by the integral of the distribution function. So this is a non-local equation, and this has been studied a lot in analysis too in connection with material science. But this is a continuous mean field model because now I'm no longer sensitive to the collapse time of each individual drop. I'm now looking at the overall distribution of drops in a macroscopic system. And just to compare the discrete mean field model to this continuous mean field model, let me plot the average mass as a function of time. So in the discrete mean field model, this average mass is going to have a spike each time one droplet collapses. But in between collapses of droplets is going to be given by a continuous property. And it's going to be monotone decreasing until one drop collapses and it's removed. Then I change the n, and then I kind of restart, and this evolves continuously again until the next drop collapses. Versus this evolves continuously in time and is monotone increasing, meaning the droplets, on average, the droplets always grow in mass as they kind of merge, as they kind of more droplets collapse and the mass gets redistributed among fewer, larger droplets. So this, I always like kind of pointing, I like this graph because here I'm approximating a monotone increasing continuous function by a monotone decreasing discontinuous function that's derived from the same problem. So it kind of sounds counterintuitive, but it makes sense if you're looking at short time scales and microscopic dynamics versus a larger length scale and time scale, looking at the overall system properties. Okay, so almost at the end. So the distribution function itself can be written as a similarity form. You can find a similarity form which corresponds to looking for a stationary distribution for long times. So for long times, whatever initial conditions you start with, the distribution of droplet sizes approaches a specific form. Or that's still somewhat argued about in rigorous analysis because there are issues about the compact support of this for distribution function. But basically, the numerics I've done is kind of matched up with some asymptotic predictions we can do for mass approaching zero and the large mass limit of how many few but large drops are there in the system. But this asymptotic approach takes a very, very long time, which is not practical for many kind of real physical experiments they do in labs and other kind of practical settings. So it's actually interesting to look at the transient dynamics that happen for moderate times. And so the transient dynamics tend to be very sensitive to the initial conditions that you start with. So in the early stages where we have the flat film destabilizing and breaking up into droplets, so are the droplets almost of uniform size and uniform spatial distribution, or if you start with a different perturbation to a film and different parameters for the thickness, then the droplets may start with a much more heterogeneous distribution of sizes and much more spatially distributed in a non-uniform way. So this is called a spinodal decomposition versus heterogeneous nucleation for initial conditions. So let me kind of focus on this one because this will have more interesting dynamics, because here you can kind of imagine this distribution function would correspond to having a large number of small droplets and a small number of larger droplets. So that may look like a bimodal distribution function. So let me start with something that looks like that. So here my axis is going to be mass versus number of drops, and these are a series of pictures of the distribution function, early time, later, and then zoomed in. So the velocity always tends to say the small drops decrease in size while the large drops get bigger. So the rich get richer as the small get eaten up. So all of the small drops are going to propagate to mass equals zero as the large drops collect the mass. That's what's happening here as the separation between small and large drops gets larger, and eventually these drops all vanish all at the same time. And in terms of like keeping track of number of drops versus time, I'm going to get a long plateau where all of these drops are sticking around, none that has disappeared yet, and then when they've gone off this cliff, all of them disappear, and there'll be kind of a mass extinction, an avalanche. And then there'll be just the large droplets left. The large droplets actually are very competitive. They don't like each other. It's a winner-take-all. So large droplets will start to differentiate among each other, and then the super rich will start pushing the rich out. So the rich will kind of start being pushed towards mass zero as the super rich kind of fight for who's going to be the final person to stay. But we'll have long plateaus where nothing happens, then a sudden mass extinction, then maybe a long plateau where nothing happens. And so this is kind of an interesting transient behavior called staircasing. And this is actually a sustainable transient response, meaning that you can see more than one of these stair steps depending on what your initial conditions started with. Like you may have several levels of large, medium-sized, smaller, and smaller drops, which will correspond to several stair steps like this, until there's only like one drop left at the end, the final winner. But the interesting thing is, you may think that this behavior seems to clash with that coarsening rate prediction that was rigorously derived by Cohn and Otto I mentioned before. But this actually doesn't clash with that because their prediction was actually on an average coarsening rate. So this instantaneous zero coarsening rate and infinite coarsening rate is actually okay with that because actually, if you do the simulations over a longer time, it does average out and is bounded by their prediction, which is kind of very non-intuitive. So this is a prediction that's kind of very different from something close to the dynamics they're expecting, but it's very consistent with that. And so I'll just close by saying a couple words about open problems and further things I'm working on in this kind of class of problems. But I hope I've shown you that there's a lot of different things that kind of go into different parts of this dynamics of studying these fluid films. So one thing that Bernard asked about is like, what happens if I have gravity back in the system? So this actually introduces transients that change the shape of the drops. So the parabolic droplets eventually get pulled down when they get too tall, and they become what's sometimes called pancakes or puddles, because puddles of water are actually pancakes because they'll be a finite thickness, and then they'll have like rounded edges. But the transient dynamics is different for the initial parabolic droplets and slows down for these larger drops. But I've studied this with a former graduate student, and now with current students, I'm also studying different kinds of more accurate coarsening models for the dynamics of like very small droplets in the initial stages. And I'm also interested in something I completely skipped over in this talk, is like what happens if you don't have collapses dominating, but you have the droplets interacting by collision. So they're very mobile rather than losing mass or gaining mass that quickly. So there are those different time scales. Another very non-obvious effect, but it's very practically oriented, is what happens if you have these kinds of dynamics happening over slow, long time scales in non-conservative systems, meaning problems where you have evaporation or condensation. Then you actually lose some of those predictions that Cohn and Otto had about their predictions were crucially related to conserving mass. So if you have evaporation or condensation and you're gaining or losing mass, then some of those predictions don't hold anymore. So models that have evaporation will have the basic equation again, but then you have an extra term for like a flux based on like the change in temperature between the surrounding air with possible condensation, water vapor. So will mass move? Will mass condense from the air to make a thicker film, or will the film lose mass due to evaporation? And with a current graduate student, Hangji Ji, we've been studying several versions of this kind of model and found interesting new dynamics in different classes of solutions. So that's all. So thank you for listening.
Thank you very much. More questions?
So thank you for the talk. So I found that you fight the singularity at the contact line with having the ultra-thin films between the droplets, if I'm correct. Why not those thin films are not subject to the rupture themselves that happen?
That's a good question. And the form of this disjoining pressure actually introduces a new height scale. So if the film is thicker, is like order 1 or thicker than this asymptotic parameter epsilon, then the film will want to kind of break up and rupture. But this epsilon can be rigorously shown to be a kind of a lower bound or something order of epsilon. If the film gets down to here, then you can show it's going to be stable, and it's not going to be able to go below this for this kind of form of this disjoining pressure. So this is a regularizing term that actually guarantees global existence, because if it really ruptures to 0, then you can't continue the PDE solutions. But with adding in this term, the dynamics changes and it starts to evolve this kind of way rather than just going down monotone decreasing.
And also, have you done work with roughness in it, and is that important for this, like having the roughness in the substrate?
So I have not, but that's a very good question, and that's a very important effect. There are many people that have been kind of studying, not just have been studying the influence that you would have in chemically patterning the solid material properties. So just having like changing, effectively like making this epsilon a spatially dependent function. But surface roughness would also probably have a strong influence on the dynamics and effectively changing the contact line of this. So, but I haven't studied that. But I can find references that I can point you to if you're interested, where other people have started doing that. But I don't think that much has been done in that direction. But that's an area for more further work.
Thank you.
Thank you.
The last few I guess years we've seen these spectacular videos on YouTube of these super hydrophobic materials and these sprays to make things super hydrophobic. For those settings, do these models work really well or do they work less well?
So extending these models to superhydrophobic materials is an important challenge, but they don't work off the bat. So these models assume, the derivation of them assumes slowly varying small gradients. Superhydrophobic, this is not quite a superhydrophobic picture, but in a superhydrophobic material, the droplet could look like actually an entire sphere resting on the surface. So you would no longer have a graph of a function as the solution. You'd have to have like the real Stokes equations for this interface. So there would need to be some other kind of approximation to kind of reduce that into some kind of effective form. So but those are the right questions. That's the kind of direction that people want to be able to extend these models to handle superhydrophobic conditions.
Okay. Thank you. Are there any more questions?
I got a couple. This is Juan Restrepo, now from Oregon State. Hi, Tom.
Oh, hi, how are you?
Good. Very nice talk. Just one quick one, which is, so the kappa that appears in the evaporation term, I gather, is just to avoid a singular behavior in the equations? That's thing plays?
So that's actually a physical effect. At the moment I don't remember. So, but that term represents a physical effect. If you're really carefully modeling evaporation, that term, I don't remember. It's probably not latent heat, related to latent heat or related to kind of some stored energy. But that is real models of evaporation have that. But in the kind of generalized model that Hangji and I have studied, we've actually eliminated that term and looked at the kind of singular behaviors that can happen when I kind of take that to go to zero and look at different balances between the conservative fluxes and non-conservative fluxes. And our article has kind of just appeared online, so you can get it from Physica D. But we've shown that by playing some games with making this term destabilizing instead of the physically stabilizing term, we can actually kind of break the assumption I told you that the epsilon regularization will prevent rupture, and this evaporation can actually cause rupture, and that's a way that's unexpected for what should be the physical model for this kind of mathematical form.
And another, I think so for that extreme hydrophobic case, would a Wiener-Hopf transformation perhaps allow you to continue pseudo-analytically through a case that is not looking like a function, but more like a graph?
That's very interesting. I never thought of that, but that's an interesting idea.
Yeah, so it might work. I mean, it's still sort of a cheat, but you can get you can push it a little harder, and at least the 2D case you can get some mileage on that one.
The only thing that reminds me of that, there was a paper by Craig Evans in SciAm at one point where I never kind of made the connection to this exactly, but there's a paper by Craig Evans a while ago in SciAm where he considered solutions of the heat equation for graph-valued initial conditions, so for multi-valued functions as initial conditions. So but that's a very good idea. I should take a look at that.
Yeah, it might work out.
Mm-hmm.
If there's no more questions, let's thank our speaker again. Thank you very much, Tom. That was a wonderful talk.
Okay. Bye.
Bye.